These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Let's talk about atoms with no formal charges. So let's think about a carbon with no formal charge. How many bonds does a carbon with no formal charge have?
4.
How many lone pairs does it have?
None.
Very good. How about a nitrogen with no formal charge? How many bonds does it have?
3.
And how many lone pairs?
1.
How do you know? Well, if you remember in general chemistry, you go over the techniques for figuring out the Lewis structure for elements. So you could use techniques from general chemistry to work this out. That's really not the best way to do it in OChem. In OChem, it's best kind of just to have it memorized. So perhaps you just have memorized that that's what a neutral nitrogen looks like. All right. How about how many bonds does a neutral oxygen have?
It's 2.
And how many lone pairs?
2.
So you might notice a little bit of a pattern here. Notice that I'm trying to set these up like they are in the periodic table. Nitrogen is to the right of carbon and oxygen is one column to the right of nitrogen in the periodic table. Notice the pattern as we move one column to the right in the periodic table, we lose one bond and gain one lone pair. And then we move one column again and we lose another bond and gain another lone pair. Notice that all of these, when they're neutral, have complete octets because there's 2 electrons in each bond. So here there's 8 electrons. Here there's 6 electrons in the bonds and 1 lone pair, which is 8. And here there's 4 electrons in the bonds and 2 lone pairs, which is also 8. Good. Now, to the left of carbon in the periodic table is an element we haven't talked about as much, boron. So how many bonds and lone pairs does a boron have? This probably might not be obvious, but why don't you take a guess and then we can talk about it. How many lone pairs and bonds do you think a neutral boron has?
5 bonds.
Okay. So that's just a guess because we haven't talked about it much. 5 bonds probably wouldn't make sense because how many electrons would that be?
That would be 10 electrons.
10 electrons. But remember, there's the octet rule. Elements in the first row can't have more than 8 electrons. Okay, well, I just said to take a guess. It turns out that actually boron has 3 bonds. And it has 0 lone pairs when it's neutral.
Mm-hmm.
Again, you could use techniques from general chemistry to prove this, but maybe it's best just to memorize it. So how many valence electrons does boron have in its 3 bonds?
6.
That's right. So notice boron has an incomplete octet. Elements that are to the left in the periodic table sometimes can have incomplete octets. Carbon, nitrogen, and oxygen were all able to have complete octets, but boron is going to have a incomplete octet. Okay, so that might just be worth memorizing. So these are the elements that we'll need for this section of the course. Now remember, these were all atoms with no formal charge. So let's move on now and talk about atoms with positive formal charges. So let's start with a carbon with a positive formal charge. Do you happen to know how many bonds and how many lone pairs does a carbocation have?
3 bonds and 1 lone pair.
Very good. Again, you could prove that using general chemistry, but Maybe you just have it memorized. What was your answer again? How many bonds and how many lone pairs?
3 bonds and 1 lone pair.
Ah, all right. Actually, that turned out to be incorrect. It has 3 bonds and no lone pairs.
Okay.
After all, does the positive charge mean that it has more or fewer electrons than usual?
Fewer.
So one way to have fewer here is that it has only 3 bonds and no lone pairs. Okay, again, you could prove this using general chemistry, but perhaps we should just memorize that. Okay, very good. So this is what's called a carbocation. Now, another element we'll need is nitrogen with a positive charge. A nitrogen with a positive charge, it turns out, has 4 bonds and no lone pairs. If you use techniques from general chemistry, you can prove that that gives it a formal charge of +1, but maybe we'll just memorize that. Do you notice, let's see. Okay, good. So notice basically to go from here to here, what happened here is we took 1 lone pair and turned it into a bond, and that increases the positive charge. And how about an oxygen? Well, it's going to follow the same pattern as nitrogen. We're going to take one of the lone pairs from the neutral atom and turn it into a bond. So in that case, how many bonds would an oxygen with a positive charge have?
3.
And how many lone pairs?
0.
Now, what we did here is we took 1 lone pair and turned it into a bond. If we start with 2 lone pairs and we turn one of them into a bond, that still leaves us with 1 lone pair.
Mm-hmm.
This can all be proved with general chemistry techniques, but maybe for OChem it's best just to kind of memorize the patterns. Can you tell, does oxygen here have a complete octet?
No.
Well, how many electrons are in the 3 bonds?
6.
And how many electrons in the lone pair?
8.
Well, 2, and that adds up to 8. Good.
Mm-hmm.
So I would say that is a complete octet, right?
Mm-hmm.
Notice that even though it has a positive charge, it still has a complete octet. It's possible sometimes to have a positive charge even with a complete octet. How about let's try the nitrogen. How many valence electrons does this have total in its bonds and its lone pairs?
4. It's 8.
So does it have a complete octet?
Yes.
Yeah. How about the carbon? How many valence electrons does the carbon have?
6.
So does it have a complete octet?
No.
No. So the only 2 things we've had seen so far with incomplete octets are neutral boron and carbon with a positive charge. Okay? Everything else has had a complete octet. Good. By the way, what do we call an ion with a positive charge? Do you remember what's the name for an ion with a positive charge?
Cation.
That's right. Good. The way I remember that is that this looks like a positive ion. The T kind of looks like a plus sign, if you see what I'm saying. So a cation is a positive ion. So, for example, this is a cation. And this is a cation. And this is a cation. However, there's also a term carbocation. What's the difference between a carbocation and a regular cation?
It's a carbon.
Yeah. So is this a carbocation?
No.
How about this?
No.
How about this?
Yes.
Yeah. Okay. So what we reviewed here is a carbocation has 3 bonds and no lone pairs. These other cations have different patterns. Okay, very good. And then we also have to focus on carbons with negative charges. Do you happen to know, take a guess, how many bonds and lone pairs would a carbon with a negative charge have? So that would be a carbon like this.
Carbon with... Is it 3 bonds and 1 lone pair?
It's kind of an unfair question because we haven't gone over the Gen Chem to solve this, but that was the right answer. That was the right answer. 3 bonds and 1 lone pair. It should certainly make sense that it's going to have more electrons than the carbocation. So the way it has more electrons is by having a lone pair that the carbocation didn't have. So a carbon with a negative charge has 3 bonds and 1 lone pair. Good. So does this have an incomplete octet or a complete octet?
Complete octet.
Because there's 6 electrons in the bonds plus 2 in the lone pair brings us to 8. All right, I think these are the only examples we'll have to go over for this section of the course. So we only saw 2 things with incomplete octets, boron that's neutral and carbon with a positive charge. Everybody else, even when they have a charge, has a complete octet. By the way, we just talked about something with a negative charge. So what's the name in chemistry for a negative ion?
Anion.
Good. How can you remember that? Well, you could say it's a negative ion. So just as a memory aid, this looks like a negative ion, N for negative, and a positive ion. The T looks like a plus. Good. What's the difference between a regular anion and a carb anion?
Carb anion is just a carbon with a negative charge, and then an anion is just any other element.
Right, or a carbon with a negative charge. That's right. Good. So what we have here is not just an ion, but we talked about a carb anion. Okay, good. Okay, so this is a table that some of these I think we didn't know already. So you might have to do some memorization to learn these. You might also see sulfur. Now, I didn't write sulfur down because you should be able to figure it out from this table. Do you have a periodic table with you, or do you know from memory? What column is sulfur in? Say sulfur is in the same column as which of these elements?
1 second. Sulfur is 16.
So which of these elements is in the same column? Oxygen. That's right. So how many bonds and lone pairs would you expect a neutral sulfur to have?
2 bonds, 2 lone pairs.
Just like oxygen. And how many bonds and lone pairs would you expect a sulfur cation to have?
I would expect it to have 3 bonds and 1 lone pair.
Just like this oxygen here. Okay, so I only wrote down the elements in the second row. But if any elements come up that are from the third row or below, you should be able to figure out how to handle them by just asking what column of the periodic table they're in. Okay, 1 moment. Good. Okay, so the next thing we have to go over for this topic is the number of hybridized orbitals and hybridization. So hopefully you've heard of this idea that an atom could be sp3 hybridized. If an atom is sp3 hybridized, how many hybridized orbitals are there? I'm not sure if that question makes sense, but take a guess. How many hybridized orbitals are there in an sp3 atom?
This was first semester, I think. Is it 3?
So let's discuss that. What does this notation mean? It means, hybridization means mixing. Mm-hmm. And this tells us what we're mixing. We're mixing 3 p orbitals and 1 s orbital. So how many orbitals are we mixing total? 4. 4 mixed orbitals. Remember, hybridized just means mixed. So in this case, we'd have 4 hybridized or mixed orbitals. The letters here tell us how many orbitals we're mixing or hybridizing together. So this is 1s and 3p. Okay, so let's try another example. If an atom is sp2 hybridized, what's the number of hybridized orbitals?
3.
One s orbital and 2 p orbitals makes 3 overall. And the other type of hybridization that's covered in OChem is sp hybridization. So what's the number of hybridized orbitals here?
1 second.
Sure, take your time.
Is it 1p and 1s?
Very good. So what's the total number of hybridized orbitals?
It's 2.
That's right. I don't think that's super hard, but notice if you weren't careful, it would be easy to make a mistake. Does sp3 mean 3 hybridized orbitals? No, it means 4. Does sp2 mean 2 hybridized orbitals? No, it means 3. So notice that these numbers don't tell you directly the number of hybridized orbitals because it only counts the p's. You also have to add in the s. But otherwise, that shouldn't be a super difficult idea. Okay, so the next thing we need to do is we need to be able to figure out the hybridization of an atom. So it turns out that for figuring out hybridization, there's a rule. For determining hybridization. But as is often the case in OChem, there will also be an exception to the rule. All right. We'll go over the rule first. So the rule is something that you learn in the first semester of organic chemistry. So this should kind of be reviewed, but we might have forgotten this. So the rule here is that the number of hybridized orbitals equals the number of attached atoms plus the number of lone pairs. Tell me when you have that written down. Are you still writing? Or are you ready?
I'm ready.
Okay, that's fine. Don't mean to hurry you. Since I can't see you, I just wanted to be sure. Take your time.
Okay.
Okay, all set. So let's look at some examples of what this means. So for example, let's work on this nitrogen. How many atoms are attached to the nitrogen?
3.
And how many lone pairs does the nitrogen have?
1.
That's something we were working on earlier. So the total is 4. 4 hybridized orbitals. Well, what type of hybridization is that? sp3, sp2, or sp? Which of those would give us 4 hybridized orbitals?
sp3.
So that's the way it works. So now we know this is sp3 hybridized. Okay, good. I'll give you another example. Let's focus on this carbon. So take your time. How many atoms are attached to this carbon? How many atoms are attached to that carbon?
3.
Which one? That sounds good to me. Who's attached to the carbon? What types of atoms?
A hydrogen, a carbon, and a carbon.
Yeah, a hydrogen, a hidden hydrogen, and 2 carbons. So there are 3 attached atoms. And how many lone pairs does this carbon have?
None.
None. We covered that earlier. A neutral carbon has 4 bonds and no lone pairs. So that carbon has no lone pairs. It doesn't matter that it's double bonded. A neutral carbon still has no lone pairs. So what's the total? I'm sorry, you were saying?
I'm sorry. It's just, this is a part of, is this part of what we're learning for the next problem set?
Oh, yeah. So these are all the techniques that we need. So the next problem set is about determining aromaticity, right?
Oh, okay, yeah, okay.
Okay. So one of the steps that you need to go through for aromaticity is to determine hybridization.
Okay.
Okay. Yeah. So I should have explained that's the reason why we're covering these ideas. Okay.
Okay.
So let's see. Where were we? So here this gives 3 plus 0 is 3. So that means there's 3 hybridized orbitals.
Mm-hmm. It's sp2.
So it's sp2. Remember, we were talking about this example, this carbon. It has 3 attached atoms, 2 carbons and a hydrogen, and no lone pairs, 3 hybridized orbitals, so it's sp2. Now, notice then in our rule here, the key thing is, notice we're not counting the bonds. We're not counting the bonds, we're counting the attached atoms. You can see why that's important here. This carbon has 4 bonds, right? 1 bond to carbon, 1 bond to the hidden hydrogen, and 2 bonds to this carbon. So it has 4 bonds, but I didn't write the number 4 down here. We're not counting the bonds, we're counting the attached atoms. So this is a good example of showing why it's important to account the attached atoms and not the bonds. Okay, good. So that's the rule we'll be using. The number of hybridized orbitals is equal to the number of attached atoms plus the number of lone pairs. So now it's your turn. What's the hybridization of this carbon?
sp3.
Good. How many attached atoms?
4.
And how many lone pairs?
None.
So it's sp3. Good. What's the hybridization of this carbon?
sp3.
Good. How many attached atoms?
3. 4.
1 carbon and 3 hidden hydrogens. And how many lone pairs?
None.
4 hybridized orbitals means sp3. Good. What's the hybridization of this carbon?
sp2.
How many attached atoms?
3.
And how many lone pairs?
None.
3 hybridized orbitals means sp2. Very good. What's the hybridization of this atom?
sp. There's 1 lone pair. Yeah, 1 lone pair, 3 atoms. Is it sp2?
How did you work that out? So how many attached atoms are there?
There is 2.
The 2 carbons?
Yeah.
Now, keep in mind, remember we did that table at the beginning. This is a carb anion. Do you remember, or you can go back and look in your notes, how many bonds does a carb anion have?
3 bonds.
3 bonds.
So, yeah, it's the 2 carbons and then the hydrogen.
So there must be a hidden hydrogen. Notice you can't figure out how many hidden hydrogens there are in bond line notation unless you're familiar with this little table here. If you know this table and you know that a carb anion has 3 bonds, that allows you to figure out that there must be 1 hidden hydrogen. Without that table, we can't figure out the number of hidden hydrogens. Okay, so to try again, how many attached atoms are there on that carbon?
3.
And how many lone pairs?
1.
Because the table we worked on before told us that. So what's the hybridization?
Hybridization is sp3.
Okay, so it looks like this one we got incorrect originally, but now we have the correct answer. That's going to be sp3. Good. So let's try doing the hybridization of this atom.
It's also sp3.
How many attached atoms?
3.
And how many lone pairs?
1.
So 4 hybridized orbitals means sp3. Excellent. Let's try the hybridization for this atom.
So there's 3 attached atoms. Oh, wait a minute. There is 2 attached atoms. Scratch that. There's 3 attached atoms and no lone pair. So it's sp2.
Sounds good. What are the 3 attached atoms?
Hydrogen and 2 carbons.
Great. How do you know there's 1 hidden hydrogen? Well, if you know this, what we talked about here, you know it. We talked about how carbocations have to have 3 bonds and no lone pairs. Well, we're already showing 2 bonds, so there must be a 3rd bond for the hidden hydrogen, and that shows that your reasoning was correct. So what is the hybridization of a carbocation? What's
hybridization of that's a sp2.
That's what we just worked out. Yes. Carbocations are always sp2. Okay, good. So what's the hybridization of this carbon?
Also sp2.
Good. So how many attached atoms are there?
3.
Including the 1 hidden hydrogen, and how many lone pairs?
There are none.
That gives us 3 hybridized orbitals, which is, what did we say was the hybridization?
sp2.
Okay, good. Okay, let's work out the hybridization of this atom.
There's 3 attached atoms and 1 lone pair, sp3.
Because we know from our earlier work that neutral nitrogens have 1 lone pair. Good. So that would be sp3. Excellent. Let's try this atom.
2 lone pairs and 2 attached carbons. That's sp3.
Good. We know from our earlier work at the beginning that neutral oxygens have 2 lone pairs, even though we didn't draw them in this case. So notice that it's perfectly possible to be sp3 even with a lone pair. Okay, very good. All right, let's try this atom.
It has 2 attached carbons and 2 lone pairs, sp3.
Okay. Now, what's the formal charge on this nitrogen?
I'm sorry. There's 2 attached carbons and 1 lone pair.
So the hybridization is
sp2.
How do you know there's 1 lone pair? Well, that's from the table we talked about at the beginning. Neutral nitrogens always have 1 lone pair. Doesn't matter whether they're double bonded, single bonded, triple bonded. If they're neutral, they always have 1 lone pair. And 3 bonds, as this does have here. Okay, good. Let's work out the hybridization of this atom.
That has 3 attached bonds and no lone pair, sp2.
3 attached atoms and no lone pair. Okay, good. We know there's no lone pair from the table we went over before, but you can also see from common sense there's no room for a lone pair because there's already 8 electrons in the bonds. So this must, what did we say was the hybridization?
sp2.
Good. Let's Let's work out the hybridization of this atom.
That has, let's see, it has two atoms connected to it, one lone pair. sp2.
That's right. So an oxygen with a positive charge has 3 bonds and 1 lone pair. We're already showing the 3 bonds, and then there's the 1 lone pair. So that would be sp2. Excellent. Let's try this atom.
That has 2 bonds, no lone pair, sp.
Good. Except instead of saying 2 bonds, we should say 2 attached atoms, because there's 4 bonds, but there are 2 attached atoms, so this would be sp hybridized. So that was correct. Good. And let's try this atom.
Three attached atoms. No lone pairs, sp2.
Okay, very good. So this is the unusual element that we talked about at the beginning. Boron is to the left in the periodic table, so it can actually have an incomplete octet when it's neutral. So we saw it has no lone pairs. So this actually would be a sp2 atom. Good. What's the hybridization of this atom?
That is sp3.
Because how many attached atoms are there?
4.
And how many lone pairs?
There are none.
Okay, so these are some important examples of hybridization. These don't cover all the possible examples for hybridization, but they should be sufficient for this section. Okay, good. All right, well, we can't congratulate ourselves too soon on mastering the rule for hybridization, because as I mentioned before, unfortunately, there's also an important exception to the rule for hybridization. So the rule for hybridization is how you learn how to do hybridization in the first semester of OChem. But in the second semester of OChem, there's an exception to the rule. So here's the exception. If an atom A has 1 or more lone pairs, and B is connected to an sp2 atom, then the atom is also sp2. So go ahead and copy this exception down into your notes, hopefully kind of close to the rule for hybridization. Tell me when you have that written down, and I'll give you some examples to try to explain what this means.
Okay, 1 second. Okay.
Okay. Now, this might seem unfamiliar, But like I said, that's because we didn't need it in the first semester. In the first semester, all we learn is the rule for hybridization. It's only now in the second semester that we're going to need this exception. So let me give you some examples to show what I mean by that exception. Okay, so what is the hybridization of this atom? And for this, we can just use the rule for hybridization.
That is SV2.
Now, here, notice, does this atom, now we're going to do this atom. Does this atom have any lone pairs?
No.
You might want to think about that a little bit more. Here we have a carb anion. So do carb anions have lone pairs?
Yes, one lone pair and three attached.
Remember, carbocations have no lone pairs, but carb anions have a lone pair. A neutral carbon would just have 4 bonds, but charged carbons fall into these 2 categories. Okay, so you can see why we had to go over this exercise here of learning the lone pairs on atoms. It turns out to be important to know when an atom has a lone pair. So that the most important part of this table is it's important to know when an atom has a lone pair. Okay. So does this atom have any lone pairs?
Yes, one lone pair.
So it meets this. And is this atom connected to an sp2 atom?
Yes.
Yeah, so it meets that. So according to our exception, this atom is also sp2. That doesn't match the rule. The rule would have said it's sp3, but the exception takes precedence here. So that's an example of how the exception works. Because of these 2 things, this atom would be sp2. So let me show you another example. Okay, so let's try this example. Does this atom have any lone pairs?
1, yes.
Is this atom connected to any sp2 atoms?
No.
So the exception does not apply here. The exception does not apply, and we just use the normal rule. So we can practice that rule. According to the rule for hybridization, what should be the hybridization of this carbon?
SV2, right now?
Yes, in this picture.
That's SP3.
Because there's how many attached atoms?
2 or 3.
Including the hidden hydrogen. And how many lone pairs?
1.
So you were right, it's sp3. So notice the exception didn't apply here. Here we just use the rule. So let's work on this carbon. Is this carbon attached to any sp2 atoms?
Yes.
It's attached to this sp2 atom. Does this carbon have any lone pairs?
No.
So the exception does not apply. Notice the key word here is and. The exception only applies if both of these things occur. So we're just going to use the rule for hybridization here. So let's practice that. According to the rule for hybridization, what should be the hybridization of this carbon?
sp3.
Okay, so hopefully these 3 examples here show you when you do use the exception and when you don't. The exception only applies if you've been able to check off both of these 2 conditions, 1 or more lone pairs and connected to an sp2 atom. So how should you do these problems now? What I would suggest is you should always check the exception first. The exception takes precedence to the rule. So first, check if the exception applies. And if it does, you know it's sp2 and you're done. On the other hand, if the exception does not apply, that's when you have to count the number of hybridized orbitals using the rule. So the best way to do problems now is first check if the exception applies. If the exception does apply, you automatically know the atom is sp2. If you saw the exception does not apply, then you can use the rule for determining hybridization. So hopefully you'll have that in your notes, and you can refer to that as we do a few more examples. So what is the hybridization of this carbon?
That hybridization is sp3.
Well, when you're ready, you can tell me what was your reasoning.
It has one lone pair.
Now let me interrupt you. Remember that now we have to have a new problem-solving technique. Our new problem-solving technique is first, you have to check if the exception applies. Only if the exception doesn't apply should we check the rule. So first check, does the exception apply to that carbon?
Yes.
Okay, so what then? What's the hybridization of the carbon?
sp2.
Okay, so we're going to have to break our old habits a little bit from the first semester. In the first semester, we didn't have to worry about that exception, but now we do. First, we check for the exception. Okay, so let's work out the hybridization of this carbon.
That's also sp2.
Because of the rule or the exception?
The exception.
Yeah, it's got a lone pair and it's connected to an sp2 atom. Very good. What's the hybridization of this carbon?
That is sp3.
Because of the rule or the exception?
Because of the rule.
Yeah, the exception doesn't apply because it's not connected to an sp2 atom. And what's the hybridization of this carbon?
That is sp3 also.
Because of the rule or the exception?
The rule.
Yeah. The exception doesn't apply because there's no lone pairs on that atom. Okay, very good. So using the same approach, let's figure out the hybridization on this atom.
This is one lone pair and connected to an sp2, so it has to be sp2.
Excellent. So did you use the rule or the exception?
We use the exception.
That's right. Because of the lone pair and because it's connected to an sp2, the exception kicks in and we don't need to bother with the rule. So this would be sp2. That's very good. How about this atom?
That is sp3.
Good, because of the rule or the exception. Would this be sp3 because of the rule for hybridization or the exception?
That's the rule.
Right. The exception doesn't apply because it's not connected to an sp2 atom. So here's where people tend to get confused. It's hard for people to understand why this is sp3 and this is sp2. Normally we would consider a neutral nitrogen sp3. Normally we consider a neutral nitrogen sp3, but not when it's connected to an sp2 atom. When it's connected to an sp2 atom, it's also sp2. So this is a particularly important example here and here. These are cases where things were sp2 that we would normally consider to be sp3. Okay, good. So let's determine the hybridization of this nitrogen.
sp3.
Because of the rule or the exception?
The rule.
Excellent. Good. I think this is a tricky one. How do you know the exception doesn't apply? After all, this is sp2, so why doesn't the exception apply?
There's no lone pair.
That's good. That's another important example here. So yeah, the exception doesn't apply. You can see there's no room for any lone pairs because the nitrogen already has a complete octet in its bonds. Good. Okay, so what's the hybridization of this oxygen?
That is sp3.
Because of the rule or the exception?
The rule.
Excellent. And what's the hybridization of this oxygen?
sp2 because of the exception.
That's right. It has a lone pair, and it's connected to an sp2. This is another important one to highlight. A lot of people would expect this to be sp3, because that's what it would have been in the first semester. But now we know about this exception, we can see in this case it's actually sp2. Good. What's the hybridization of this atom?
sp2.
It turns out that both the exception and the rule agree here. The exception and the rule both agree that that would be sp2. Good. What's the hybridization of this atom?
1 second.
Sure, take your time.
There's a lone pair. Yeah, sp2.
Both because of the rule and the exception. The rule and the exception agree here. Either way, it would have to be an sp2 hybridized atom. This is another example that comes up a lot in the problems here. Okay, good. So now we'll go on and see how to apply this. So let's review what we've been talking about so far. So first of all, what is the rule for hybridization? How would you describe in words, what's the rule for hybridization?
It's the number of attached atoms plus a number of lone pairs.
Equals what?
Equals the hybridization.
Equals the number of hybridized orbitals. Yeah.
Okay.
Number of attached atoms plus number of lone pairs equals the number of hybridized orbitals. And when you know the number of hybridized orbitals, you can figure out the hybridization. Okay? And then what's the exception to the rule for hybridization? How would you describe that in words?
If an atom has one or more lone pairs and it's connected to an sp2 atom, then the atom is also sp2.
Excellent. That's perfect. So when you're doing a problem and you want to figure out the hybridization, what should you check first? Should you check the rule first or the exception first?
The rule first.
It actually turns out, as remember, it turned out it makes more sense to check the exception. The exception takes precedence, right? The point is, there's no point counting up the attached atoms and lone pairs if the exception applies. If the exception applies, then the atom is automatically sp2. Maybe I presented this confusingly because I went over the rule first. But even though we went over the rule first, when you're actually doing a problem, it's better to check the exception first. Because if the exception applies, there's no need to check the rule. Okay, so to review, if you're trying to figure out the hybridization for an atom, should you check whether the exception applies first or should you apply the rule first?
The exception first.
Okay, good. That's what you must have been doing on these problems here, and we were getting those correct. Okay, we'll have more chance to practice that as we go on. It would be good to go back and redo the examples I just did. It's important to be able to get all of these right quickly and easily. So these would all these examples would be good to go back and try again, covering up the answers to make sure you can get them right quickly and easily. So moving on, what we're going to be studying here is what's called a cyclic pi system. And we're going to have to count the number of electrons in the cyclic pi system. So here's the rules and techniques for doing that. Rule number 1. Each atom contributes at most one set of pi electrons. Each atom in the ring contributes at most one set of pi electrons. So, since we're focusing on cyclic pi systems, we're almost always going to be focusing on a ring. So, the only atoms that can contribute are the atoms in the ring. Rule number 2. If an atom has a pi bond, it contributes the pi bond. It contributes the atom in one pi bond. So the cyclic pi system. So, for example, in this case, atom 1 and 2 are both contributing the same 2 pi electrons. The electrons in the pi bond. Even though we're going to work on cyclic systems here, I'm only going to draw part of the ring to make this clearer right now. So this atom here is going to contribute I changed my mind again. So in this case, there would be 6 pi electrons. 2 electrons in this pi bond, 2 electrons in this pi bond, and 2 electrons in this pi bond. Okay. Does that make any sense?
Yes. Is that a triple bond?
Yes. So in this case, there are 8 pi electrons contributed in the cyclic cycle. 8 electrons in the cyclic pi system. Notice I'm only counting one of these pi bonds because of rule number 1. Each atom can contribute at most one set of pi electrons. Each atom contributes at most, this is the key, each atom contributes at most one set of pi electrons. So these 2 atoms have already contributed one pi bond. They can't contribute the other pi bond because that would break this rule. So this is the tricky part right here. So if an atom has a pi bond, it can contribute the atoms in one pi bond. But if there's two pi bonds, it can still only contribute the atoms in one of the pi bonds, because you can contribute at most one set of, pi electrons. Okay, so do you see why I'm saying then that these electrons here are going to contribute 2 electrons and not 4 electrons?
Mm-hmm.
Okay, good. So now we're ready to move on to rule number 3. If an atom has no pi bonds and it has if an atom has a pi bond and it has one or more lone pairs, it contributes the electrons from the pi bond. Not from the lone pairs. Tell me when you have that written down.
Okay. Wait, I'm sorry. Okay.
So let's count the pi electrons here. It turns out that in this case, there are 6 pi electrons. 2 from this bond, 2 from this pi bond, and 2 from this pi bond. The key is we don't count the lone pair. Because, remember, each atom can contribute at most one set of pi electrons. Rule 1 is the key. Each atom can contribute at most one set of pi electrons. Well, this nitrogen is already contributing pi electrons from the pi bond, so it can't contribute more from the lone pair. So these don't count as pi electrons. Okay, so does that make sense? Do you see how I ended up with 6 pi electrons here?
Yes.
Okay, good. All right, so this is an example to show what rule number 3 meant. Rule number 4. If an atom has no pi bonds and it has one or more lone pairs, it contributes 1 lone pair. So tell me when you have that written down.
Okay. Okay.
So how many pi electrons are there here? Well, there's 2 pi electrons in this bond, 2 pi electrons in this bond, and then this lone pair, those are also pi electrons. So that would give us 6 pi electrons. Make sense?
Yes.
Why didn't this lone pair count as pi electrons? Well,
It was already contributing.
from the pi bond. That's right. The pi bond takes precedence. But since this doesn't have a pi bond, it can contribute the lone pair. So is it possible for a lone pair to be pi electrons?
Yes.
Yeah. But is it guaranteed that a lone pair is pi electrons?
No.
No. You have to check for a pi bond first. Okay, good. So if you remember the rules, this oxygen must have 2 lone pairs. So
Right.
how many pi electrons are there here? Well, there's
6.
Okay, great. Very good. That's right. Excellent. There's 2 pi electrons in the pi bond. There's 2 pi electrons here. And we could count this pair as also pi electrons. But can this pair also be pi electrons?
No, if one is already considered.
Because remember, the key rule, each atom can contribute at most 1 set of pi electrons. Each atom contributes at most 1 set of pi electrons. So if we've designated this lone pair as pi electrons, this lone pair is not pi electrons. Of course, if you wanted to, you could have called this lone pair the pi electrons, and then this one would not be pi electrons. So as I think you already figured out, this now has 6 pi electrons. All right, so what we just went over here, let me put an asterisk. These 3 cases are the ones that give people the most confusion. I'm putting an asterisk just to show these are the most important that give people confusion. People don't realize how these are different. So a lot of people, for example, look at this example and they say, aha, lone pairs are pi electrons. But then they can't understand why this lone pair is not pi electrons or why this lone pair is not pi electrons. So hopefully now we see the pattern between these. Lone pairs sometimes can be pi electrons, but not when there's a pi bond on the atom. And you can only have 1 lone pair on each atom that counts as pi electrons. Okay, good. Excuse me. So that would be rule number 4. It looks like we're time for rule number 5. Seems like a lot of rules, but with practice it's not too hard to apply these. So rule number 5, if an atom, well, rule number 5, only lone pairs and pi bonds can ever count as pi electrons. Nothing can be a pi electron except lone pairs and pi bonds. So, how many pi electrons are there in this molecule? Well, there's 2 in this bond, 2 in this pi bond. How many pi electrons is this carbon contributing?
None.
Very good. That's right. Because we know it doesn't have any pi bonds, and from our earlier work, we know it has no lone pairs. This is why it was important earlier to learn that carbocations have no lone pairs. So therefore, as a result, this is going to have 4 pi electrons. Okay, so those are our 5 rules. Very good. I should make a note here. These are rules for rings with an sp2 atom. sp2 or sp atom at every atom in the ring. Those are rings that are called completely conjugated. So these rules only apply when the ring is completely conjugated. An sp2 or an sp atom at every atom in the ring. But that's the only type of example that we're going to need to deal with in this chapter. So for the examples in this chapter, these are all the rules that we'll need. Okay, good. Okay. Do you have those rules in your notes?
Yes. Yes.
Okay, great. Thanks. Okay, so now we're ready to start seeing how to solve problems. So it turns out that there are 3 different types of categories that we're going to be breaking molecules into. There is a category that is called aromatic. There's a category that's called anti-aromatic. And there's a category that's called non-aromatic. Okay, it's not super logical to me how there could be a 3rd category that's neither aromatic or non-aromatic, but even though the names are not logical, those are the names that are used. Okay, so what does aromatic mean? Aromatic molecules are unusually stable. An aromatic molecule is unusually stable. That means it's more stable than you would normally expect from its Lewis structure. An anti-aromatic molecule is unusually unstable. That means less stable than you would expect from its Lewis structure. So anti-aromatic means unstable, aromatic means stable. And non-aromatic means normal. It has the same stability you would normally expect from the Lewis structure. So in the first semester, we basically worked with non-aromatic compounds. So non-aromatic means just like the normal compounds we worked with in the first semester. And aromatic and anti-aromatic are 2 new types of compounds that we're now introducing in the second semester. Aromatic is unusually stable, anti-aromatic is unstable. Okay. So what does aromatic mean?
Aromatic means stable.
How about anti-aromatic?
Unusually unstable.
Good. And how about non-aromatic?
Normally stable.
That's right. So I find that oftentimes it's helpful to kind of personify the molecules. So which category would be the particularly happy molecules?
Stable molecules.
Yeah. So which category? Aromatic, anti-aromatic, or non-aromatic?
Aromatic.
Great. And which type of molecule would it kind of make sense to think of as unhappy?
Anti-aromatic.
That's right. Good. So which types of molecules would you expect to be the most reactive?
Anti-aromatic.
Yes, because if you're unhappy, you want to change into something else. And which type of molecule would be the least reactive?
Non-aromatic. Or, I'm sorry, aromatic.
Yeah, aromatic. Because if you're very happy, that means you're not reactive. After all, we said aromatic means stable. Well, stable means non-reactive. And then non-aromatic is always kind of in the middle. Non-aromatic is always more, well, all right, it tends to be in the middle of these 2. So what you're going to have to do on the problems on the exam is you're going to be given a molecule, and for each molecule you have to decide, is the molecule aromatic, anti-aromatic, or non-aromatic? And then do that for another molecule. So here's how we figure that out. First of all, we split this up into 2 sides. In order to be on the left side, let's see. First of all, the molecule has to be a ring. The fancy word for a ring is cyclic, but we could just call it a ring. So if you're not a ring, you must be non-aromatic. Number 2, the molecule is supposed to be flat. The fancy name for flat is planar. But we could just say it means flat. So flat means like a piece of paper, right? A piece of paper is flat, but if you crumple up the piece of paper, it wouldn't be flat anymore. Okay, so if the molecule is not flat, it would be non-aromatic. However, this is a little tricky. In your course, it's beyond the scope of the course to try to figure out whether a molecule is flat or not in this section. So on the problems you're going to be doing, you should just basically assume that all the molecules are flat unless you have a good reason not to. When you're given problems, you should just assume the molecules are flat unless there's a really strong clue that it's not. You should just assume that the molecules are flat in this course. Okay, so this isn't going to be very important for solving problems. Also, to be on this left-hand side, we need to have sp2 or sp atoms at every atom in the ring. That's one reason why we spent so much time practicing hybridization. We need to have an sp2 or an sp atom at every atom in the ring to be on the left-hand side. So if there is an sp3 atom in the ring, that would be automatically non-aromatic. Okay. So if the molecule is not a ring, what category is it in? Well, it would be non-aromatic. If the molecule is not flat, what category would it be in?
Non-aromatic.
Right, although, like I said, that's not going to come up in your course because you're going to be assuming everything is flat. If there's an sp3 atom in the ring, what category would it be?
Non-aromatic.
Right. So what if it's a ring and it's flat and there's an sp2 or sp atom at every atom in the ring? What category would it be then? Well, either aromatic or anti-aromatic. So there's one more rule for figuring this out now, which is to count the number of electrons in the cyclic pi system. Before I forget, I meant to mention, what's the fancy name for Rule 3? sp2 or sp atoms at every atom in the ring, that's called completely conjugated. So in class, your instructor probably said that the molecule has to be completely conjugated. But the easier way to check for that is just to check the hybridization. So when your instructor says that the ring has to be completely conjugated, what they mean is sp2 or sp atoms at every atom in the ring. So I'll write it down in the way that's more useful for solving problems. But in class, this is usually called completely conjugated. Okay, so now we have to count the number of electrons in the cyclic pi system. Well, that's good news because we just learned how to do that a few minutes ago. So if there are 2 or 6 or 10 or 14 electrons in the pi system, that makes it aromatic. If there are 4 or 8 or 12 or 16 electrons in the cyclic pi system, that makes it anti-aromatic. Now, do you see the pattern in these numbers? Study these numbers. What should be the next number in this sequence? What goes here?
Hold on. Sorry.
Yeah, I'm sorry. Take your time. Take your time. Go ahead and write this down and tell me when you're ready to continue.
Okay. What was your question?
Study the numbers in this sequence. See if you can see the pattern here. Try to find the pattern. What should be the next number in this sequence?
18.
There you go. And then what?
22.
Great. And then what?
26.
So what's the pattern? The pattern is start with 2 and then keep adding 4s. That's how you get the numbers in this sequence. Start with 2 and keep adding 4s. Okay? Well, let's try to do the same thing for the numbers in this sequence for anti-aromatic molecules. See if you can find the pattern here and then tell me what number goes here.
20 and then 24.
Very good. And the next number?
28.
There you go. So what's the pattern here?
Start with 4 and then add up 4.
Yeah, start with 4 and add 4. So notice in both cases we keep adding 4. You add 4s here and you add 4s here. If you're adding 4s in both lists, what's the difference? The difference is where you start. If you start with 2 and you add 4s, you're going to get a different list than if you start with 4 and you add 4s. Okay. So that's how we figure out which of these 3 categories we're going to be in. Now, by the way, what's the fancy way of describing this list? Well, the fancy way of describing this list is that in class they probably said that this list is 2 plus 4n. Excuse me. But we're not going to really need that for solving problems. That's just a fancy way of generating this list. All this means, this is just a mathematician's fancy way of start with the number 2 and then add 4s. So this is just a fancy way of summarizing this list. It starts with 2 and then you add 4s. So we won't really need that because there's an easier way to memorize the list. And then in class you might have seen a fancy way to describe this list is this. So this is just a fancy way that a mathematician would use to describe this list. This is just a formula that says that to get the numbers in the list, you start with the number 4 and then you add a bunch of 4s. Well, we already saw that was the pattern. Start with the 4 and add a bunch of 4s. Okay, so I wanted to mention these because I'm sure you saw this in class. But the main point I'm making is that as far as the test and the homework is concerned, you can forget about these rules. We don't need to use either of these rules for the test or for the homework because they're just fancy ways of describing these lists. And it's much easier to describe them in words. This list is start with the number 2 and add a bunch of 4s. And this list is start with the number 4 and add a bunch of 4s. So we don't need those fancy 2 plus 4n or rules. We can just use this. Okay, so now we're ready to proceed. So let me give you a few examples of how this approach would work. So for example, so let's try to figure out what category this molecule falls into. Well, it is a ring. And remember, we're just going to assume that everything is flat.
Mm-hmm.
However, notice this is sp3. Or is it? What is the hybridization of this carbon?
That is sp3.
Yeah, the exception doesn't apply, so it's just a normal sp3. So this rule wasn't satisfied. So what category is this in?
Non-aromatic?
Yeah, this is non-aromatic. Here's something that's very important. Notice, if it's non-aromatic, it's pointless to bother counting the pi electrons. If it's non-aromatic, there's no reason to count the pi electrons. So what do you do first? Do you check these 3 things first, or do you count the pi electrons first? You should always check these rules first, because if we fall into this category, it would be a waste of time to count the pi electrons. Okay? Okay, so let's try this. This is a ring. We're always going to assume the rings are flat. There is an sp2 atom at every atom in the ring. And how many pi electrons are there in this molecule?
6.
So it looks to me like it would fall in which category?
This is aromatic.
Because 6 is in this list. By the way, what's the name of this molecule?
Benzene?
Yeah, so you might already have known benzene is the most famous and the most important aromatic molecule. So we're just confirming here or proving what you might have already known from class. Benzene is certainly an aromatic molecule. Okay, good. Okay, so your turn. Try this example. You can try working this out on paper if you like. Try to figure out what category that molecule is in.
There are no lone pairs, but that is an sp2. This is 2,4. This is non-aromatic. I'm sorry, this is anti-aromatic.
So what's the hybridization of this carbon?
sp2.
Because of the rule for hybridization. Good. So we're over here, and how many pi electrons?
4.
So what was your answer again?
This is anti-aromatic.
You were right. Good. That molecule is anti-aromatic. Excellent. That's exactly how you do it.
This is much easier than the way he taught us in class.
Good. I'm glad to hear it. But you can see, I hope it feels easy, but there was certainly a lot of preparation work, right? You can see why sometimes this is confusing in class, because there really is a lot of preparation you have to do before you're ready to do the problems. But now that we've done the preparation, the problems hopefully won't be super hard. There's quite a few variations we have to go through, but once you've done the preparation, these shouldn't be a super hard part of the class, which is good because we just finished the hardest part of the class, right? We just finished proton NMR. That's probably the hardest part of the class, so we want a little bit of a break here. All right, so let's see. Okay, now let's try this example.
Is that non-aromatic? Hold on a second, sorry.
Take your time. Go ahead and take your time. So this is the part where we learn how to do the problems for the test. So just take your time and work these out on paper, and then as you're ready, you can report your results to me. We'll do a whole bunch of examples of this because we know there's going to be a bunch of these on the test.
This is sp2. This is anti-aromatic.
Okay, so what's your reasoning? What's the hybridization of this carbon at the top?
sp2. Because of the exception.
Because of the exception. Excellent. So by the way, does this have any lone pairs?
Does that have any lone pairs? Yes. No, doesn't actually. No, not at all.
So no lone pairs?
Mm-hmm.
Okay, well then the exception couldn't apply, could it?
Wait. Let me check my notes, sorry.
Mm-hmm.
It has one lone pair, actually.
That's why the exception applies.
Yeah.
Okay, good. Okay, so that's pretty important. That's the exercise that we did here. Carbanions have one lone pair. Remember, again, if we were going to be really virtuous about this, we would have learned how to figure that out using general chemistry skills. But instead, we're going to be kind of lazy and just try to memorize this table here. So one thing we'll have to do is memorize which of these have lone pairs and which ones don't. Okay, so moving back here. So what have you decided? What category is this in?
That is not as anti-aromatic.
Okay, so how would we work that out? How many pi electrons are there?
There are 4 pi electrons.
And so are you counting these two here?
Oh, I forgot about that. So it should be aromatic.
How many pi electrons are there?
6.
Okay. Why did you count 4 before?
I only counted the pi bonds.
And not the lone pair.
Mm-hmm.
Okay. All right. All right. So we're congratulating ourselves a little too quickly on how easy we made these. These really do take some practice. It's easy to make careless mistakes, so that's okay. We'll do some practice here. Okay. So what did we decide? How many pi electrons?
I'm sorry, what?
How many pi electrons are in the molecule?
There are 4. Pi electrons, there are 6.
So what category is this?
This is aromatic.
Okay. So pi lone pairs can definitely count as pi electrons, as we saw earlier. Lone pairs can definitely count as pi electrons. Okay, well, take your time and try to apply the same approach here. Let's figure out what category this is.
This is also aromatic because it has 6 pi electrons, and all of them are sp2.
The nitrogen is sp2 because of the exception, and it has a lone pair. So there's 1, 2, 3, 4, 5, 6 pi electrons. Excellent, we got that one right. All right, try this problem.
This is also aromatic.
How many pi electrons?
6.
This oxygen up here has what hybridization?
That has sp2 hybridization because of the exception.
That's right. Now this has 2 lone pairs.
One of them is counted.
But only one of them is counted. We talked about that before. Because you can only contribute 1 set of pi electrons. That's the fundamental rule. You can only contribute 1 set of pi electrons per atom. So only 1 lone pair counts. This is the one to asterisk. This is one that people tend to get wrong because they accidentally count both, or they don't understand why they shouldn't count both sets of pi electrons. Okay, excellent. Let's try this example.
Oh, I have to look back at my notes. I want to say that is antiaromatic.
So what's the hybridization of the boron?
Is it sp2?
Because of the rule for hybridization. How many lone pairs does the boron have?
None.
Right. How do you know? Well, we went over that at the beginning of the session today. Notice that means boron, since boron is towards the left of the periodic table, it actually has an incomplete octet. It only has 6 valence electrons. So how many pi electrons are there in this molecule?
4.
That's why you're right. It is anti-aromatic because the only pi electrons are in the bonds. How many pi electrons is the boron contributing? None. Okay, so you worked that out correctly. The key is that for the test, we need to have memorized that the boron has no lone pairs. Good. Okay, let's try this example.
This is non-aromatic because one part is sp3, the top carbon.
Okay, good. I was trying to trap you there. I gave you a whole bunch of ones that were all sp2 at every atom in the ring, but you didn't fall for the trap, so that's good. This is sp3 hybridized. It's no lone pairs, so the exception doesn't apply, so it's non-aromatic. So here's a trick question. The trick question is, how many pi electrons are there in this molecule? And the answer is, who cares? We don't need to count the pi electrons when it's non-aromatic. It sounds like you got that right. So there's no point even counting the pi electrons once you see it's non-aromatic. Okay, so this is, I think, one of the trickiest ones to watch out for. I'm putting an asterisk here. It's really easy to forget to check this rule number 3. You always have to check rule number 3. Your instructor does put in problems where there is an sp3 atom somewhere in the ring, so you always have to check this. 95% of the problems satisfy rule 3, so it's easy to get lulled into complacency and forget to check this. But that's certainly something that's likely to come up on the test, so it's good. It's good that you were not lulled and you actually were checking. Good. Let's try this. Okay, try this example.
This is aromatic.
What's the hybridization of this atom?
This is sp2.
Because of the rule and the exception. Good. This does have a lone pair. How many pi electrons are there here?
2.
So how many pi? What's the total number of pi electrons in the ring?
6.
So do we count the lone pair as pi electrons?
No.
Okay, excellent. This is the hardest example for students. This gets a big asterisk. So that's good that we got this correct. This is the one that students almost always get wrong. It's really hard for them to understand why we're not counting this lone pair. But I think we've done the preparation work to see why now. Remember, the fundamental rule is each atom can contribute at most one set of pi electrons. Each atom can contribute at most one set of pi electrons. The nitrogen is already contributing the 2 electrons from the pi bond. So this lone pair is not pi electrons. Okay, so most students have trouble with that, but you did not. You got that right, so that's good. That would be a good problem to review as well.
It's time to wrap it up, John.
Can I have 10 more minutes?
Yeah.
Thank you.
Okay, good. So let's see, moving on to here. So let's try this example.
Okay. I would say this is non-aromatic. Actually, hold on a second. Actually, no. This is.
Take your time.
This is aromatic because there is an exception for the sulfur, and there are 6 pi bonds.
Pi electrons. Okay.
Pi electrons. Sorry.
So what's the hybridization of the sulfur?
sp2.
Because it has some lone pairs.
Mm-hmm.
So are these lone pairs pi electrons?
Yes. Just one.
But only one set can be pi electrons. So there's a total of 6 pi electrons in the ring in that case. All right, excellent, very good. I hope you can read my writing here. This one's hard to draw. Okay, try this example.
I would say this is aromatic.
Okay, what's the hybridization of this atom?
sp2.
Because of the rule. And how many pi electrons?
6.
Good. How many pi electrons does the carbocation contribute?
None.
None. But it's still sp2, so the molecule is still completely conjugated. Good. So we got that right. By the way, remember, what does aromatic mean?
It's stable.
That's right. Now remember I said it meant more stable than you would ordinarily expect. Are
Right.
cations usually stable?
Cations are.
What's
Yes.
better? What's better, a cation or neutral?
Cation.
I'm not quite sure why you said that.
Oh,
So does
I'm sorry,
nature
neutral.
like or dislike charges?
Dislike charges?
Yeah, so what's more stable, neutral or a cation?
Neutral?
Yeah, so we're not saying this is a very stable molecule. It's not that stable a molecule. It's just more stable than most cations, is the point. That's why aromatic means more stable than you would normally expect. This is not particularly stable because it's a cation, but it's more stable than most cations are. It's more stable than we would normally expect for a cation. Let's try this example.
This is aromatic.
What's the hybridization of this atom?
sp2.
Because of the exception. And this one?
sp2.
Because of the exception. So it is sp2 hybridized at every atom in the ring. Good. And how many pi electrons are there?
6.
Because does this have any lone pairs?
Yes.
Yeah, carbanions have lone pairs. Is this pi electrons?
Yes.
Yeah, that counts as pi electrons. This counts as pi electrons. This is pi electrons. So it looks like we got that one right. There's still a couple more things for us to go over here for aromaticity. Your instructor did a whole range of examples. We haven't covered every single detail on that, but we've made some good progress, and we should certainly be able to finish that topic next session and move on to the next topic. So obviously, as usual, make sure that you re-practice this material so that we can move on as quickly as possible. There's lots of examples here. Try to redo these. Also, you need to memorize this table, right? You can't do these problems without memorizing this table. There's a lot of stuff here to memorize. You got to memorize the rules. So for today, we were probably relying on our notes, but try to memorize all this so that next time we can practice this without looking at our notes. Okay, well, let's start with this. So again, the problem is we have to figure out whether this is aromatic, anti-aromatic, or non-aromatic. I guess I'll stay on my screen, but you can tell me what answer you get.
Okay. This is aromatic.
How many pi electrons?
6.
Do these count as pi electrons?
No, because it's contributing one set
Okay.
of pi bond.
Good. Excellent. All right. So that was one of the main topics that we had talked about last time. Good. Okay, here's something that looks a little bit different than the earlier questions, but we can basically attack it the same way. So let's give this one a shot. And again, we want to figure out if it's aromatic, anti-aromatic, or non-aromatic.
This is aromatic.
How many pi electrons?
10.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so when there's multiple rings, you still use the same basic approach. Even though there's multiple rings, you're still counting up all the pi electrons. So we still got to the same basic answer here. Good. Let's try this one.
It's aromatic.
How many pi electrons?
10.
1, 2, 3, 4, 5, 6, 7, 8, and these do count as pi electrons. Okay, so this is another case with 2 rings, and you got that one correct as well. What does it mean that this is aromatic? What does aromatic mean?
It's unusually stable.
Good, more stable than you would predict from its Lewis structure. Okay, that was good. Okay, let's try the same process for this example.
Non-aromatic.
That was fast. Good. How do you know?
Because one of the carbons is sp3 hybridized.
That's right. Why doesn't the exception apply to that carbon?
Because there's no lone pairs.
Okay, terrific. Good. So I was trying to trap you because we hadn't done any non-aromatics for a while, but you didn't fall into the trap. That's good. We always have to check that all of them are sp2 hybridized. Okay, something else that you and I haven't talked about yet is a molecule like this. So let me just show you the method for this type of molecule. So the key thing here is notice that now there's a pi bond outside of the ring. So it's not really clear whether we should count these electrons or not. Remember, we need the electrons that are in the cyclic structure. We need electrons in a cyclic pi system. Well, do these 2 electrons count as part of the system or not? The way to work it out is to draw the other resonance structure. Well, which way would the electrons prefer to move? Towards the oxygen or towards the carbon in the resonance?
Towards
Which is the more significant resonance structure? The one where the electrons move towards the oxygen, or is it more significant where the electrons move towards the carbon?
towards the carbon.
Let's try to work that out. Who wants electrons more, oxygen or carbon?
Oh, oxygen.
Yeah, how do you know?
Because it's more electronegative.
That's right. So should to get the most significant resonance structure, should we move the electrons towards the oxygen or towards the carbon?
Towards the oxygen.
So this is the electron pushing arrow for the resonance structure. Let's move to your screen. Try drawing the next resonance structure from that picture. I think we've gone over the rules for using electron pushing arrows, so we should be able to use the rules for electron pushing arrows to draw what that next resonance structure looks like. So try to use that arrow to draw the next resonance structure.
Okay.
Okay, done?
Yes.
Yeah. Now, I'm starting to forget what we have covered and what we haven't, but have we talked about the rules for using electron pushing arrows? How many charges should we, have we talked about how many charges do we change on every step?
Yes. 2.
Okay, good. Yeah, so that's an important thing to talk about. How many charges do we always change to? Now, when we talked about that, we were talking about mechanisms, but the very same rules apply to resonance arrows as well. Every time, so just to review, every time you're drawing a new resonance structure, how many charges should you change?
2.
2. So that really is worth emphasizing and repeating. That comes up all the time. And remember, we shouldn't have to guess about which charges to change. How did you know to change the charge of the carbon at the top of the top carbon and not one of the bottom carbons? Why is that obvious?
Because it's at the end of the arrow.
Yeah, it's at the end of the arrow. That arrow clearly shows that electrons are moving away from that top carbon. So it doesn't take too much thought to see that we're getting that positive charge. Okay, so now we ended up with that. So now, as it turned out, now how many pi electrons are in the ring?
2.
2. So let's write that down. 2 pi electrons in the cyclic structure. 2 pi electrons in the cyclic structure. The electrons, I guess there are some pi electrons on the oxygen, but they don't count because they're not part of the cyclic pi system, which is what we said matters. So would this be aromatic, anti-aromatic, or non-aromatic?
This would be aromatic.
Because 2 is the first number in our list. 2 is the first number in our list for aromatic structures. Okay, good. So that was a type of problem we hadn't talked about before, but that's the way to do that. So what do you do? What do you do when there's a pi bond poking out of the ring? How do you tell whether the pi electrons count as part of the ring or not? Well, you have to draw another resonance structure. Let me go back to my screen. That would be a good one to mark and try again. All right, here's another example. Why don't we move back to your screen now when you've copied this down. Go back to your screen and show me what would be the process for analyzing this example, please.
My goodness. Okay. And now we forgot this charge here.
Oh, what do you know? I almost forgot it too. Okay, good. How many charges should we change for every new resonance structure?
2.
2. That's always good to just keep repeating because that's one of the fundamental bases of the course. Okay, so now we know that the electrons in the pi bond don't count as part of the ring from this resonance structure, so we didn't include them, and we got an anti-aromatic number. Okay, that was a good process. It's good that you double-checked and caught that problem with the charges. I'll go back to my screen. Now, you drew the resonance structure where the electrons move up to the oxygen. How do you know that that's more significant than the resonance structure where the electrons move down to the carbon?
Because oxygen is more electronegative.
Yeah, so generally we would prefer that resonance structure. Okay, good. Let me write this down. Okay, make sure you copy this problem carefully and accurately, and I'll stay on my screen, but you can work this out on paper and then tell me what your answer is.
Well, it's non-aromatic.
How many pi electrons did you count? Or why did you say it was non-aromatic? Oh, okay. Yeah, why is it non-aromatic?
The carbon in like the top has is sp3 hybridized.
You're absolutely right. Okay, that was an inadvertent trick question, but you got it right. Okay, very good. So this would be non-aromatic. That's right, the way I drew it. So it's no point counting the pi electrons. So that's good that you checked that. Let's say that there was a pi bond here, and try this question. So that was a good catch, but now let's try it this way. So I was telling you to copy it accurately, but I hadn't been accurate in setting it up. But let's try it this way now.
This is anti-aromatic because of 8 pi electrons.
You said that how many pi electrons did you mention?
There are 8, 2, 4, 6. 10 actually, so it's aromatic.
Okay, which one did you say? How many pi electrons?
There are 10
Okay.
pi electrons, so it's aromatic.
So let's see. 1, 2, 3, 4, 5, 6, 7, 8. Were these the ones you counted?
Yes.
So this pair, is this pi electrons?
No, it's contributing the pi bond electrons.
Yeah, they're not pi electrons because it's already contributing the pi bond. But is this pair pi electrons?
Yes.
Because there is no pi bond. Do we count these electrons?
No, because they're not in the ring.
Yeah, they really are pi electrons actually, but they're not part of the cyclic pi structure. So since these don't count either. I think you already worked that out. We only count the electrons that are actually in the ring. Okay, so you can see on the test you want to double check your steps to make sure you're counting correctly, but I think your second answer was correct. 10 pi electrons makes that. Well, let's see. What was your answer? Aromatic or anti-aromatic?
Aromatic.
10 pi electrons makes it aromatic. Good. So that's a pretty complicated example, but I think you saw the idea there. Okay, so let's copy this carefully, and I'll stay on my screen, but you can tell me what answer you get.
Aromatic. It's 10 pi bonds, including the one lone pair on the sulfur.
10 pi electrons. 2, 3, 4, 5, 6, 7, 8. Now the sulfur has 2 lone pairs. Do they both count as pi electrons?
One of them does.
Yeah, only one pair counts as pi electrons because you can only contribute one pair. Okay, so remember that sulfur is like oxygen, and we use pretty similar approaches for working it out. Good. Let's try this example.
This is antiaromatic. It's 4 pi bonds, pi electrons.
How many lone pairs on the boron?
None.
Yeah, we learned that last time. So what's its hybridization?
sp2.
So this is completely conjugated. It is sp2 everywhere, but this has no lone pairs, so it's not contributing pi electrons. Okay, good. So that's the way that we deal with boron. Excellent. Okay, how about this example?
This is aromatic.
How many pi electrons?
6.
Do these count as pi electrons?
No,
No, because
the
of the
pi
pi
bond
bond.
does.
Good. Okay, let's try this one. This is a triple bond.
This is aromatic.
How How many pi electrons?
There are 6.
In the cyclic structure.
Mm-hmm.
So can we count both of these pi bonds as pi electrons?
No, just one.
Yeah. They're both pi electrons, but only one of them is in the cyclic structure. How do we know? Well, we just memorized you can only contribute one set of electrons to the cyclic structure. So if this is in the cyclic structure, this wouldn't be. So that would give us 6 overall. Okay, good. Well, it looks like you got that. Obviously, you should do all the problems in the homework to double check all of that. There might be a couple other quirks we haven't gotten to, but I think we made good progress on that material. That's very good. That's a good recollection of the stuff we went over last time. Looks like that's pretty sure to be on the test. Okay, so for review, let's try one of these problems. So try this, you can do this on your own piece of paper. Try working out on paper, is this aromatic, anti-aromatic, or non-aromatic? Actually, why don't we work this out on your screen?
Okay. This is aromatic.
Okay. It looks like you did not count the electrons in the carbonyl pi bond. Why not?
Because they're not part of the ring.
How do we know they're not part of the ring?
Because they're actually, you would have to do resonance.
That's right. So that's the best thing to do here. So try drawing electron pushing arrows to show how you would form a new resonance structure from that picture, and then draw the new resonance structure. Okay, looks like we're having some trouble with that. Let's go back to my screen to talk about that. So there's 2 different directions that we could conceivably move the electrons in this pi bond. We could move them into the ring or away from the ring. Well, which one should we do? We should draw the one which will give us the more significant resonance structure. So the question is, which way would these electrons rather move, towards the nitrogen or towards the oxygen? What do you think?
Towards the oxygen.
That's right. How do you know?
It's more electronegative.
That's right. Now, I think that's the opposite of how you were drawing it a second ago, though. I think you were moving the electrons into the ring. But in this case, the more significant resonance structure pulls the electrons out of the ring. After all, that's the whole reason we're doing resonance here. Our whole question is, are these electrons part of the ring structure? Remember that we only want to count the pi electrons that are a part of the cyclic pi structure. Well, these electrons, it's not clear whether they're part of the ring structure or not. The whole point of drawing the resonance structure is to determine whether they are part of the cyclic structure or not. Well, it's going to be a more significant resonance structure to move them away from the ring than to move them into the ring. So we want to draw a resonance arrow that looks like this to get the more significant resonance structure. Okay, so we can fix that this is the correct arrow to draw. And now let's go back to your screen, and you can try drawing the resonance structure that results from that arrow. Remember that we've learned that the arrows tell us what to do. If we just take our time and follow the rules, the arrows should tell us exactly what changes to make in order to get the new picture. So take your time and try to use that arrow to draw the new resonance structure. Okay?
Okay.
All right, good. How many charges do we change for every new resonance structure?
2.
And you did change those 2 charges, so that's great. So how did it turn out? Did the electrons in the pi bond end up being part of the ring structure or outside the ring structure?
Outside.
Outside, as you might have been guessing before, but we can only confirm that by actually drawing the more significant resonance. When there's a pi bond extending out of the ring, you always have to draw that new resonance structure. So that would be a good thing to practice there. You have to draw the resonance structure that's more significant. So how many pi electrons are in the ring now? So in our new picture, in our new resonance structure, let's recount how many electrons are in the ring.
So you said recount how many pi bonds or pi.
We just need to redetermine now. So the previous resonance structure could not really be used to determine whether the molecule was aromatic, anti-aromatic, or non-aromatic. You can't determine that while there's a pi bond extending away from the ring. You have to draw a new resonance structure that clearly shows that those electrons are either in or out of the ring. And now we have to just go through our normal process and count how many electrons are part of the cyclic pi structure, just like we would always do for this type of problem. So how many electrons are part of the cyclic pi structure?
6.
Okay, good. So I'm not saying that what you got before was incorrect. It was just that we were using a method that wouldn't be reliable. First, we have to draw the new resonance structure, and then we can see how many electrons are in the ring. So we decided there were 6 pi electrons, so what category would this be in?
Aromatic.
Good. By the way, for your notes, you should go back and change the 6 pi bonds to 6 pi electrons. And I'll go back to my screen. One, two, three, four, five, 6. And we don't count the lone pair on this nitrogen because it's already contributing the pi bond. So there's 6 pi electrons in the cyclic pi structure. So we said this was aromatic. Okay, so this would be a good technique to review here. We didn't quite use the best method the first time around. When there's a pi bond extending out of the ring, we have to draw a new resonance structure. How do you decide which resonance structure to draw? The more significant resonance structure will move the electrons towards the more electronegative elements. That would be a good problem to review. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.